Very good evening, everyone, and welcome to the Hibiscus Coast Astronomical Society meeting, Introduction to Astronomy. And tonight we've got Chris chatting to us about stellar corpses, which is a great one. And then I'll be kicking off the news tonight, as Josh was quite busy this week. And hopefully at the end, if we've got time, I'll put up Stellarium and we'll have a look at what's going on in the world.
I'll leave and go back in.
What?
I'll leave and go back in.
Sorry, it looks like we're having some issues here.
Sure.
Okay. No, there we go. Okay, so I will kick off now with the news. Okay. So the first thing that we have in the news today is the SpaceX and NASA launch, which went off with great fanfare. Initially we had a bit of a delay, but I think everything went perfectly on when they actually did launch. So what's fantastic about this is like almost 9 years since a manned rocket took off from US soil, and this is also the very first private space company who has provided launch facilities for NASA. So NASA's Doug Hurley and Bob Behnken were in the Dragon capsule on top of the Falcon 9 rocket, and they lifted off at about 3:20 p.m. And it was funny enough, that's exactly the same launch pad that was used to send the Apollo crews to the moon. So if it looked familiar, indeed it is. So up they went, and they docked with the International Space Station. That's sitting about 250 miles up above the Earth, and a successful docking there, except one of them, I think it was Behnken, knocked his head on the porthole of the door when he came in, so he sort of got a little bit of a bang on the head. Funny enough, that's exactly what happened with me yesterday. But there you go. So they are planning to spend between 1 and 4 months up in space before coming down again. It is not, we're not yet sure who's going to come down and when they're going to come down. So all in all, a really, really fantastic flight. For me, I really loved those brand new spacesuits. They were quite good. And I don't know if you saw the inside of the capsule. Instead of the old Apollo levers and buttons and lights flashing, there they had a beautiful, nice big touch screen control panel in front of them. So I think it's very, very space agey to me. So well done there. So if you're really into rockets, it's a good chance to see a Kiwi launch. That's the 11th of June. It will be taking off between 4:45 and 6:30 from Mahia Peninsula. So if anyone is up for a good trip, that will be a nice destination to go now that lockdown's over. Having been there relatively recently, it is quite a long way to get there, so it's definitely not a day trip. But yeah, if you go, take photos and let us know. So one of the exciting things this week was it was the biggest solar flare since 2017. As you've seen in the news, the sun's been pretty quiet with very, very few flares. So this is a pretty good one, and this could be a sign that the sun has entered the new solar cycle. But we'll have to sort of see in the next sort of coming weeks whether that's actually the case. So we're at the minimum at the moment, solar minimum, and we're expecting to tip over from cycle 24 to cycle 25. But of course, with the sun, we just never know exactly when that happens. But this is a really strong indicator that we are well on track to starting cycle 25, and that means more and more of these solar flares and sunspots taking place. It's actually not a very strong one. It was N.1.1 on its the scale. The scale's from 1 to 10. So quite a small one, but good enough to make an impact on what we are seeing in terms of the solar cycle. Another exciting one is Proxima Centauri b has been confirmed as being our closest exoworld. Now, a couple of years back, 2016, they discovered that there was this planet called Proxima b, and but it was very, very kind of murky. It wasn't really confirmed until recently. So the ESPRESSO team have just confirmed it, and they've also confirmed quite a lot of the statistics. So we know it's a very similar size to Earth, a mass of 1.17 Earth masses. It orbits its star in only 11.2 days, which is pretty quick, but it is quite a lot closer to their star. Proxima Centauri is, of course, a red dwarf, which means a habitable zone is much, much closer than our habitable zone is. So where it is located, it actually receives about the same amount of solar energy from its sun that the Earth does. So what does this mean? It means theoretically Proxima Centauri could have water on the surface, and it could be habitable. Of course, we wouldn't know details about that quite yet in terms of temperature, composition of the planet's atmosphere, that sort of thing. And of course, the big one is radiation. Red dwarfs kind of are known to emit lots of solar flares, and that makes living on one of these planets quite interesting because it's so close to the sun. So by all accounts, really, really interesting. What is also interesting, that popped up in the news, I didn't make a slide for this, is that Proxima C has just been found, and I was looking at old Hubble data from about 11 years ago. So it's quite an interesting thing there that we've got two planets, exoplanets discovered or confirmed within a week of each other. So if you have a look there, there's a picture of what sunset looks like on Earth and what it could look like on Proxima b. So pretty similar, just a bigger sun. So astrophysicists have come up with a new class of transient objects. So Chris has mentioned the cow before as a transient object, and basically it's a highly luminous family of cosmic explosions. The most famous, what we call F-bot, was known as the cow. It was quite a rare event that appeared to show the birth of a black hole or a neutron star. So just recently they have found another one of these ones called CSS 161010. What's interesting is that you initially see these in the light spectrum, so people actually saw it in the optical range, and then all the radio signals come through shortly after that. The gas and particles from these F-bots is quite amazing. It's about 55% the speed of light, which is incredibly, incredibly fast. And we don't usually see that anywhere in nature. But yeah, it's quite amazing. They also release a huge amount of gamma ray bursts, and but it's only the mass that they release, about 1 millionth the mass of the sun, is nothing. So very, very interesting objects these. If you want to know more about F-bots, just Google it online. There's a lot written about it, and it's something to keep an eye on if you're interested in sort of new objects out there. So here's one where one mystery has helped solve another mystery. So the first mystery that we're talking about is the fast radio bursts. As you know, these have been in the news quite a lot recently because no one knows what they are. They're mysteries. However, by monitoring these mysteries, we've actually discovered where the universe's missing matter is. So we're talking about dark matter, where astronomers previously have found that there's a whole lot of matter, dark matter, missing in the universe, and they couldn't really make head or tail of that. However, using this monitoring of fast radio bursts, they actually discovered that each of the bursts was quite spread out and slightly delayed depending on the frequencies they were monitoring. So higher frequencies are our first, lower frequencies later, and they realized that this must be due to the missing matter that's found between galaxies. And of course, most of these FRBs are from other galaxies. So it is quite an unusual thing that a mystery has actually solved one of the mysteries. They say that using the same method, they could actually start to probe the cosmic web of matter, which is a lattice of diffuse material thought to be strung between the galaxies. So they're looking at trying to track down about 100 FRBs. If they can find 100 FRBs, they can then really sort of test where this matter is in the whole universe. So quite an exciting one there. Another very interesting discovery is astronomers looking back in time, 11 billion years ago to be exact. They've discovered a rare type of galaxy. This is described as the cosmic ring of fire. You can see a picture of it there. The galaxy is roughly the mass of the Milky Way, and it has a circular hole in the middle, like a gigantic space donut. And it's quite interesting, though, that that hole in the middle has a diameter 2 billion times longer than the distance between the Earth and the Sun. So a huge, big thing that. It's been called R5519, and it's quite interesting because it shows us what the galaxies looked like right in the beginning, right near the Big Bang. So this is about 3 billion years after the Big Bang. So we're looking back 11 billion light years ago, and this is another 3 billion before that, before the Big Bang. So relatively new little galaxy that. So quite interesting as well is that there's quite a lot of star formation taking place within the ring, and that also sort of shows us kind of what was going on way back then, and sort of where galaxies and how they've evolved over time. So I found that one pretty interesting. Here's another one that I found quite interesting was the Very Large Telescope. It's the European Southern Observatory's VLT telescope. Have found one of the signs of an early star system being born. So they found this star AB Aurigae, which has this very dense cloud of dust and gas around it. You can see it there on the left. But as they zoomed in, they found there was this little section here that was taking place. And on further investigation, it looks like a little planet is forming just over there. So there's all this matter which is going into the planet, and there's a little bit that's been released out the side there. So that's the point of where the planet is. Of course, the star sits about there, which they've blocked out, so we can see the detail. But yeah, that's the very, very first little planet that's forming. Now, this is quite amazing. This is actually the very first time we've had our direct evidence of a baby planet coming into existence. So very important when we look at sort of planetary evolution and solar system evolution, that we can see these things actually happening out there. So quite exciting to see. The image of the week is the detailed view of the Milky Way. Now this I posted onto our Facebook group. So if you haven't seen it, if you give me 1 second here, I will call it up. There we go. So I'll zoom out. So that's the picture there. And you can zoom in quite a lot if you have a look at all those billions of stars taking place. And you can zoom right in and zoom right out again. And what's interesting is if you look at this image, you can pick a spot like almost anywhere and you find something interesting. So I found this little spot down here. Thought, oh, I wonder what that is. Zoomed in on it. Oh, look at that. Nice little globular cluster. Absolutely pretty. Of course, 1 or 2 people have found a couple of anomalies within this as well. There's one lurking up here somewhere. Of course, these are just little artifacts that I found. There we go. If you have a look over here. So that's just a light artifact. But of course, people look at it and go, the UFOs are coming. But yeah, that's quite an amazing map. So I've popped it up in the Facebook group if you want to go and have a look there. So you click on the link, that's what it looks like. And then you can just zoom in, point and zoom in. And you just realize how many billions and billions of stars there are out there. You know, you look at our Milky Way and just pick a point and just go in and you just see how many stars there are. And of course, most of those are not the brown dwarfs either. So if we take that into consideration, there's even more. And it's absolutely mind-blowing. So there we go. That is all for the news today. So I'm going to be handing back over to Chris in a few seconds. Make sure I've got everything up here and running. Okay, Chris, over to you.
Yep, thank you, James. Am I coming through now? So if I
just go to slideshow. Yep, start from the start. Bring this up here. Bom, bom, bom. Yep. Then I come down to Zoom. I can't. You can you see the slide now? No. Okay. From the start. No, Zoom's still not coming up, is it? Share screen. That's it. Desktop.
Yeah, it's not coming up yet.
Am I coming through? No, I'm not.
So just your voice and your.
I can't hear you, James.
I think you might have me on mute. Stand by, everyone. We're just getting Chris sorted out here.
Can you hear me, James?
Yeah, I can hear you.
security issues.
Okay, it looks like Chris is having a few issues there. So, yeah, you'll have to look at my beautiful face. So, yeah, so while Chris is sorting that out, what we are going to do is I'll have a look and see if I can get Stellarium up and running in the interim. And we'll start on what's going on in the skies above. But yeah, unfortunately with this medium we tend to have a few interesting issues. Okay, so we got Chris back on. Yeah, yeah. Yeah,
Hello?
I can hear you.
Can you hear me, James? I can't hear. I might have to leave and reboot again. Something.
Okay.
Can you hear me?
Yeah, I can see you.
I can't. I can see you, but I can't hear you. Can you hear me?
Yeah, leave and come in. I can hear you.
Okay, good. Okay, that's all good. We'll persevere. Okay, Dropbox.
Okay, we're still working on this. I think Josh is going to call Chris and
Should I do that?
just try and work something out there with him.
I'm not sure I have his number.
Yeah, I can't see the screen.
Yeah.
Okay, Josh is about to call Chris there. Um, yeah, so there's a little bit of an issue there. So Chris had a bit of an issue with some security issue. So I'm just having a look. Yes. Okay, let me get Stellarium up. Sorry about that, folks. Sorry for all the quietness here. Okay, I think we've got it. Window shift left. There we go. And this is, I don't want that. So this is our night sky at the moment. Once I get, sorry, I usually do this on the other screen and then go from there. There we go. So yeah, looking from the south, we can see that Tucana is right there and Arcana is right there, right on the horizon right now. If we go forward a little bit, you'll see how they just sort of sit there. So we're looking now about 9 o'clock. So if we scoot around here to the west, you'll see things like Hydra, Leo popping up over here, Virgo sitting above. Almost directly overhead, we've got the Southern Cross, and sorry, I'm just checking to make sure you can all hear me. So just on the side, will be down here somewhere, will be Omega Centauri. To be up this side, Omega Centauri. I think that's up there somewhere. But anyway, all in that sort of area. So if it's nice and clear, you can actually pop out. There's a huge number of some nebula and interesting things across this neck of the woods here, with the Coalsack Nebula and everything else. So so there we've got the moon. The moon is right next to Antares. So Antares, as you know, is the heart of the Scorpion. This is in our winter skies. Scorpio is very predominant. So that should be an easy one to find. Look for the moon. Look to the right. Look for the bright red star, and that's the heart of the Scorpion. And then from there, it's quite easy to see the tail over there. Was going down in the east. Over here, we've got Sagittarius. Over here, with coming across, we're back to Tucana. So quite a few interesting things up there if you follow the Milky Way across. Let me see if I can get the other things up and running. Where's the deep sky objects? There we go. So if we look at the deep sky objects, we've got all the M's up here, all the various NGCs and the M's. Definitely worth having a look at some of them. You know, of course, go outside, use your smartphone, and it's pretty good usually. You can track these things down. Have a look with your telescope. And you'll see quite a lot of things up there. There's another one I quite like, the Ptolemy cluster. Magnitude 3.3, so you need a decent scope to see it, but pretty bright object. It's an open star cluster. And as you know, I'm quite into my star clusters, so I quite like that one. Of course, if you've got a relatively good telescope, you can see quite a few of these objects. Up here, Wishing Well cluster is another good one. Southern Pleiades, now that's one you can actually have a look at with your binoculars. So scoot around from, there's the Southern Cross there. So just to the right a little bit and down, and it's pretty easy to see that Southern Pleiades. So definitely worth going out and having a look just for that. So Southern Pleiades, this is not Matariki, but it looks very similar to Matariki. especially through, you'll see why through the telescope. Very, very pretty. So popping around, any more deep sky stuff, that's pretty good. So there's Omega Centauri up there. So there's the Southern Cross, there's the pointers, so about halfway between Hadar and the Cross, straight up there. Of course, that's another pretty one there. It's the Jewel Box. Open star cluster, definitely worth seeing. You need probably a decent telescope to see that. So there we go. I can hear Chris having a bit of a chat in the headphones. I'm just waiting for Josh to pop up there. So if we pop over here, there's the south again. We pop up a little bit. There's the small Magellanic Cloud up there. And of course, another really nice one to see is this one here. It's 47 Tucanae. Another globular cluster, probably my second favorite after Omega Centauri. Yeah, very good one to go and have a look through binoculars at. If you're in a very dark place, of course, both those globular clusters you can actually see with the naked eye. Of course, when your eyesight's a bit like mine, no, you can't. So I usually resort to binoculars for those two. But yeah, really pretty. And of course, once you see that through the telescope, it's pretty amazing. If we zoom in a bit here, that's 47 Tuc there. And of course, there's the Magellanic Cloud. So if we pop over here, where are we? Southern Cross. Let's zoom in on my favorite one. There we go. There we go. Omega Centauri cluster. My absolute favorite. You know, this thing is about the size of the moon. If you actually go and look, it's just, of course, very faint, so it's not as bright as the moon, obviously. But you know, once you go out and it's really dark and you see it, you're absolutely amazed, especially if you've never seen this one before, because it's so obvious. I remember, you know, I was in my sort of early 30s when I first saw it with the naked eye, and I just couldn't believe I'd been watching the stars for so long and never really seen it. So there we go. All right, we're getting a bit of an update.
Yes, issues with screen sharing, but if Chris emails the slides to you, can you open his slides and click through? He says next slide,
yeah,
as long as he can see you. Can you see him here? Is he back on?
Yeah, I can hear him.
Yeah. Cool.
Okay, so it looks like we've got another thing here. He's got a bit of an issue with screen sharing on his side, so he's going to be sending his documents over to me. Then I'll be popping them up on the screen here, and he'll be telling me when to change slides. So that's quite an quite an interesting way of doing it. So technical difficulties, I'm afraid. But there we go. So the big problem is the old moon over here, which generally wipes things out in the sort of the near vicinity. But like I say, Antares is a really good bright star, nice and red as well. You zoom in, there we go. You can see all that beautiful nebulosity around it as well. So the more you look at it in the telescope, you'll see that nebulosity around it. But you know, easily seen even in sort of the bright moon. So there we go.
Okay, so yeah, so once you're ready,
so let's have a look. Oh, there's another good one. A bit low in the sky now. It's a summer beehive cluster. Another beautiful little open star cluster. It's a bit faint. You need a bit of a stronger telescope to see this one. There we go. Let me just zoom in on that one. You know, not much to see when you sort of where was it? So it's this whole section over here. So not that many stars, but really, really pretty to have a look at you know, when you get to see it. This is one of the things, you know, when you look at the fainter clusters and the you know, even some of the funny nebula that are there. Like, yeah, we know there's Eagle. That's an Eagle. There's a Mega Nebula. There's the Eagle Nebula down here. There we go. It's quite pretty. Of course, as it's moving, that's actually the sky moving, not by funny screens. So, and that's a Mega Nebula over here.
Once you're ready, you should have the slides in the email. Chris is on Zoom now.
Okay. Yeah, so I've got the slides here. So it looks like we're going to be starting across with Chris in a second. Okay. All right, let me get rid of this. Okay, we are almost ready there. Okay. I'm going to remember to put Chris's audio on when he pops up. Okay, Josh, we are ready. Just need Chris is on mute at the moment. He can start his video as well. All good.
All good?
Yeah.
Cool. Okay, all good.
Okay, so yeah, my apologies there. We will get that sorted out. So James, have you got it on the first slide, the title slide? James is going to do the slides from his end, and I'll just give him the prompt when to move over. So thanks for staying with us, guys. Welcome for another session of an introduction to astronomy talk. So next slide, James. So tonight's talk is entitled Stellar Corpses. When a star dies, the party is not over. What that is implying is that you always use the word corpse, meaning something lifeless, dead body. But these babies and stellar corpses, they're far from it. They get up to lots and lots of mischief, just like me. They're almost like the zombies of the universe. So next slide, James. So what is required, decided, was a talk involving, you've heard of white dwarfs, neutron stars, and black holes. And I thought to myself, what is needed is a talk that encompasses those three terms, but in the context of the origins, properties, and various capabilities these guys have. So that's what we're going to talk about tonight. Okay, next slide. I'm going to look over here occasionally, guys, just to, because I haven't got the slideshow in front of me. But how I'm going to do this, I've split the talk into 5 chapters. One is a little bit of background, sort of just to bring you in the picture. 2, I'm going to talk about white dwarfs. We covered white dwarfs sort of to a fair degree last month, and so I'm just going to briefly touch upon them. You can check the meeting from last month, and it goes into a bit of depth about the activities of white dwarfs there. 3rd chapter is going to be on neutron stars, and this is where I'm going to put most of the focus on tonight. I'll talk a little bit about stellar black holes, and that's stellar black holes not to be mistaken by intermediate black holes or supermassive black holes at the center of galaxies. And then we'll have a bit of a sum up afterwards, and I'll give you some homework to do too. But the bottom message is, the bottom line throughout this thread is, the party is far from over, just because we call them corpses. Now, James, here, next slide, my friend. So it should read background. And it's I'm going to give you an overview of the stellar corpses and their properties. And then I want to talk about a really important concept, degenerative matter, because that, at the end of the day, is what these corpses are made of. So I think that's a really important thing for us to talk about. Okay, next slide, James. So a little bit about stellar fundamentals, about stars and so on. The bottom line is, when stars spend most of their life in a stable state, they are supported or propped up from the inward force of gravity by ongoing nuclear fusion in their cores, pushing outwards. And that puts them in a nice balance. And that's called hydrostatic equilibrium. That's the term given to that state. And that's how stars spend their lives, keeping themselves stable and propped up. Okay, next slide, James. So what happens at the end of a star's life, as we talk about, when nuclear fusion in the core stops? What happens is the core collapses, and all the outer layers around the core all get expelled outward into space. And it can be one of two ways. You'll see on the left there's a nice pretty picture. I haven't got my cursor to show you things, but James will show you there. That's called a planetary nebula. And you'll see that those are small to medium mass stars. And you'll see that little wee bright dot that James will point out in the middle of the nebula. That's a white dwarf. Or if the stars are bigger, as you're going to find out, those outer layers go in a big explosion called a supernova, which we're going to talk about more next month. And you'll see that supernova explosion spreading outward. Right in the middle there, that little white dot, James will point to it, and you'll see that, my friends, is a neutron star in the middle. So stellar corpses, yeah, white dwarfs, neutron stars, and we'll talk a little bit about black holes. So next thing is, what type of stars give rise to these stellar corpses? And to the next slide, thanks, James. And you'll see there, I've headed up stellar corpse progenitors. And you're probably wondering, what are progenitors? Progenitors is just the term that astronomers use to describe the original star that gave rise to the particular astronomical body. In these case, the stellar corpses, white dwarfs, neutron stars, and black holes. And you'll see there on the top row, you've got a main sequence star, and that's a star less than 8 solar masses. And a solar mass is the mass of our sun. It's a sort of a standard thing that astronomers use, and it's 2 times 10 to the power of 30 kilograms, and that's called 1 solar mass. So James will probably point out that top row I've got up there on that slide. You'll see there a main sequence star, anything up to 8 solar masses. That's still pretty big, but relatively speaking, that's considered a low mass star. Turns into a red giant, and then the core collapses down to that little white dwarf you'll see in the middle, and you can see those outer layers spreading out as the planetary nebula. And what you're left with is a naked white dwarf. Drop down to that second layer, thanks, James, and you'll see main sequence stars. And these are stars greater than 8 solar masses. And you'll see they turn into red supergiants, and then they finish their lives going supernova, exploding. And what's happening there is the core is collapsing, nuclear fusion has stopped, the core is collapsed, and the outer bits are exploding. We're going to go over more about the exact mechanisms of that next month, or the month after, when I next talk about nuclear synthesis. And you'll see what's left over in terms of the collapsed core. In a star that was originally 8 to 20 solar masses, the collapsed core ends up as a neutron star. And that's really what we're going to focus on tonight. And you'll see that stars that began their life greater than 20 solar masses, after they've gone supernova, the collapsed core is then a black hole, which I'll briefly explain later on after neutron stars. Okay, James, next slide, thank you. So yeah, here's the slide. We're going to start talking about degenerative matter. And this is a strange form of matter you don't see on Earth, and it's what these stellar corpses are made of. So let's go, James, to the next slide. And I've got there a picture of ordinary matter. And you'll see that normally nuclei, as we know them on Earth, or an atom rather, you've got a central nuclei. I've got 4 of them lined up there. And you can see the electrons that James will point out with the cursor Thanks, James. You'll see the electrons all going around in nice sort of orbits, if you will. Life's not quite like that, but that's how we imagine them, sort of orbital spaces with electrons. And those atoms are all nice and orderly, and those atoms arrange themselves in appropriate manner depending on the substance you talk. So that's ordinary matter. So let's move on to talk about degenerative matter. And there's two main sort of important concepts I want to discuss about it. One is that as that star core collapses onto itself, the forces of compression are so great that that normal atomic structure gets totally disrupted, like nothing you'd see on anything on Earth. That's important. The second important principle is called the Pauli exclusion principle. And that's just a law, if you will, of quantum physics that came up, that was first discovered by Wolfgang Pauli many years ago. And he quite correctly stated, he found with his equations, and it's proven to be true with quantum mechanics, that no two fermions are a group or a class of subatomic particles, of which electrons and neutrons are members of that group. And the Pauli exclusion principle says no two fermions, i.e. electrons or neutrons, can simultaneously occupy the same quantum state. That means sort of energy level and so on. The bottom line is they can't stack up and sort of merge together in that same space and same energy space, like, for example, light can when you're intensifying light. They've got to keep away from each other, neutrons and electrons. That's a really important concept to keep in mind as we talk about degenerative matter. Okay, James, the next one. James, take her on to the next slide. So let's talk about electron degenerative matter. Yeah, there's two different types. There's electron and neutron degenerative matter. So this refers to the core of a star of 8 or below solar masses. When that core collapses, the pressure is so great that it starts disrupting all the normal structure. And James will point to that little box I've got on the right-hand side there, which shows all the atomic nuclei. Instead of all lined up with lovely electron orbital spaces around them, the nuclei are just jam-packed. And you've got electrons just zooming, diving, darting, left, right, and center, dipping, bopping. They're just going all over the place. They're running amok, these electrons. Why are they doing that? They're obeying the Pauli exclusion principle that says no two electrons can get close enough to occupy the same quantum state. And so they're trying to keep away from one another. And what does that do? That creates a resistance, a force, a quantum force. And then that quantum force or resistance manages to support that white dwarf or collapsed core of those stars up to white solar masses. So that's called electron degenerative matter, and that's what goes up to make white dwarfs. Next slide, thanks, James. And the next slide is neutron degenerative matter, and no clues here what that's referring to. This is what's going on inside neutron stars. So as that bigger core that belonged to a star of over 8 solar masses, as that core of a higher mass starts collapsing into itself, the forces are so great of that collapse, it goes into a state initially, this is all happening in splits of seconds, it goes into the state of electron degeneracy, where all the electrons just get squashed out of the way and the nuclei get packed in together with electrons zooming everywhere. But this time, the gravitational force is greater and it overcomes that resistance of electron degeneracy. And the electrons actually just get jammed and rammed straight into protons. They merge to create a neutron. When you get an electron, merge it with a proton, which you need a lot of force to do, but there's force here to do it, you get a neutron. So what do you get? You suddenly got a big collapsed core or ball of neutrons. And what are the neutrons going to try and do? They're going to obey the Pauli exclusion principle. They're going to dip and dive and try and scurry away from one another as much as they can. And that itself creates a resistance. That resistance gives support for the neutron star. So that's pretty much what's going on in degenerative matter. And you now know what's going on inside a white dwarf and a neutron star. Okay, next slide. Thanks, James. It should be titled White Dwarfs, which, as I said, we talked in quite some depth last month, so check that out online. So just briefly, as we've spoken, white dwarfs are the core remnant of a low intermediate mass star up to 8 solar masses. Next slide, thanks, James. And you'll see there what's going on. The core is collapsed into our central white dwarf, and the outer layers now are being expelled. This process, in contrast to a supernova explosion, takes thousands of years to happen. It's usually over sort of about 10,000 years or so. Those outer layers puff out, and on to the next slide, thanks, James. And then whammo, you have this beautiful images you see on the internet, and that's called a planetary nebula. And what's going on in there, James will point out to you with his cursor, the little white dot in the middle, that's your exposed white dwarf, or your exposed core made up of electron degeneracy. Those babies are hot. They're about 30,000 degrees Kelvin, or just think of 30,000 degrees. And they're emitting a lot of high energy ultraviolet waves. And that is then ionizing and illuminating all those expelled outer layers of the stars to make them glow like they do. So that's what you're looking at there. Next slide, thanks, James. Okay, so we're now moving on to, what happens in these stars. The core nuclear fusion stops, the core collapses, and you'll see exactly there in that picture James will be pointing out down the bottom on the right-hand side there, you've got a state of gravitational compression where all these neutrons are just quietly all packed up with electrons running amok around them. And the next slide shows you the overall global picture of what a white dwarf would look like, what the models suggest they look like. And essentially it's carbon and oxygen. That's another whole talk why you get to that. Most most white dwarfs are about the size of Earth, to give you an idea, and that's got, I think, a diameter of about 12,000 kilometers. They're pretty compact and dense, such that if you got 1 teaspoon of a white dwarf, it would weigh about 15 tons on Earth. 1 teaspoon. That's how heavy, how concentrated, how dense these babies are. Their masses, they actually range from about 0.17 of a solar mass right up to about 133 solar masses. Most of them usually fit in 0.5 to 0.7 solar masses. Your average white dwarf is usually a little over half of a solar mass. In other words, that's 1 times 10 to the 32 kilograms. Interesting enough, it's counterintuitive. Normally you think of something that's got more mass, it actually is bigger. But because of this whole compression process that's going on, it's counterintuitive in white dwarfs. The higher the mass, the more compression they've been able to achieve, so the smaller they are. Just an interesting little thing. And James, next slide, thanks. Now, the thing about white dwarfs, how can they become active? And the bottom line is they come active predominantly through close binary systems. Just briefly, our sun, for example, is a solo star, and it just quietly goes around the galaxy on its own. A binary system is when you get 2 stars going around one another, a central point of gravity, and a close one, of course, means they're really, really close. If you get a white dwarf that's close to something like a red giant or a red supergiant, its outer layers of that red giant gets attracted, and James will quietly point out, you can see the outer layers getting sucked in, and it doesn't just go straight on to the white dwarf. It is attracted by its gravity because it's so dense and compact. It just grabs that material, which is mostly hydrogen, off the red dwarf. But it's just the laws of physics because of the whole rotation process that's going on. It forms a planetary disk, or an accretion disk, they call it. And that accretion disk gets really, really hot because a lot of particles are grinding round and round past one another. And what happens then, next slide, thanks, James, is that the material on the inner part of that accretion disk starts falling on to the white dwarf as its two is rotating. And with time, more and more material builds up on the white dwarf. That material gets further compressed against this compact object, gets compressed and gets heated. And then eventually it reaches a critical temperature, whammo, hydrogen fusion occurs on the surface of the white dwarf. And you get an amazing explosion. That explosion is called a nova. The word nova just means new star. So it appears as a bright new star in the sky. That's what we see. And that's what's going on there. So that's how white dwarfs in a close binary system can form a nova. Next slide, James will show us how they can form a supernova. Here you've got the same scenario. You've got the red dwarf quietly transferring material onto the accretion disk, which in turn gathers onto the white dwarf. After maybe a few novae, slowly the mass of the white dwarf is slowly creeping up. But there's an interesting thing. The laws of physics tell us that at about 1.4 solar masses, in a state of electron degeneracy, suddenly becomes unstable. Those electrons that were zooming around have to go faster and faster and faster to keep away from one another. At about 1.44 solar masses, those electrons have to approach the speed of light to avoid one another. The whole system becomes unstable, that can't happen, and the whole white dwarf goes poof and totally explodes into a massive type 1a supernova. That's the brightest event that you can see in the sky. It's, out of all the supernova, the 1a is the brightest. Have a look at last month's talk. We talk a lot about 1a supernova and the importance of them in astronomy. The other point I'll mention briefly here, the nova explosion is just on the surface of the white dwarf. The white dwarf survives it and the process repeats. This business going on here with these type 1a supernovas, the whole white dwarf gets catastrophically destroyed. It's a one-off event, pretty spectacular too. So I think that's, yeah, and the other thing, couple of other things with white dwarfs. Next slide, thanks, James. White dwarfs and close binaries can quite happily merge together. What happens when that happens? You can get a type 1a supernova, or the increased mass and compression can create a neutron star, which we'll talk about shortly. Next slide, thanks, James. We'll show you, last year, some astronomers found signs of a really oddball-looking star. It's a star, it was burning, nuclear fusion was going on, but it didn't match anything. And the computer models actually showed what it was. Two white dwarfs had merged. The end product was still less than, it didn't explode, was less than 1.4 solar masses. But what happened is nuclear fusion reignited, rekindled, started up. You had a new star, albeit an oddball star, but there you go, something different. So next slide, James will show us just a summary of white dwarfs. They are the end product of a star, a low to medium mass star, up to 8 solar masses, where the core collapses into itself, electron degeneracy, the outer layers puff off over thousands of years to form those beautiful planetary nebula. And it's where you get a close binary system with a white dwarf, you start getting those repeating nova explosions, or a one-off massive bright 1a supernova. And of course, you can get the mergers to create a neutron star or a supernova. Let's move on. That's enough about white dwarfs. So thanks, James. Next heading is neutron stars. My key message, two messages here. One is neutron stars, as you're about to see, are really small, dense, compact objects that have strong magnetic fields and they rotate extremely rapid. So they're really compact, powerful magnetic fields, and they rotate. And they have loads of fun. You think you might be having fun? Wait to see what these bad boys get up to. So I just wanted to say that right up front to whet your appetite about what we're going to be talking about. Okay, James, next slide, thanks. Just a brief review of that previous slide, the progenitor, or the original star it came from. James will point out that lower line there. We can see a large star, over 8 solar masses. It goes supernova, and if it's still less than 20 solar masses, that exposed core after the supernova explosion is your neutron star. And I put in there the masses, which will come to the mass of a neutron star. They usually vary from 1.4 to 3 solar masses. That's the core. Next slide. And James will point out to you there, that's a lovely X-ray image of the Crab Nebula in the constellation Taurus, of a supernova remnant. So in other words, a star greater than solar mass, its core, nuclear fusion has run out, the core has collapsed into a neutron star, and the outer layers of massive explosion, a rebound explosion, have ended up this big, massive supernova, and that's all the remnants of it. And James will kindly point out the little white dot you can see right in the middle there of that supernova remnant, and that, my friends, is the neutron star, the collapsed core, beaming itself out, radiating out itself in X-ray wavelengths. So that's what they look like when you're looking at, that's a Chandra telescope image, my favorite telescope. Just recapping here, what's going on with this degenerative matter, which you all know about now. So that core of normal matter going on with nuclear fusion. It collapses under its own pressure because it can't hold itself up anymore. The nuclei in the atomic, the electron sort of orbital spaces all get totally deformed and squashed out. You've got increased mass going on here, so then it even drives harder, pushes those electrons into the protons to create a condensed ball of neutrons, all trying to run away and scurry away from each other, which keeps a general resistance and force going, which holds it up. So everything I've written here, you've got a soup of free neutrons zooming around, obeying the Paulite exclusion principle. Okay, James, next slide. Thank you. So yeah, here's a little bit about neutron stars, a little bit more about them. So as I mentioned, they're about 1.4 to 3 solar masses. So they're significantly, if you will, roughly say twice, 2 to 3 times the mass of a white dwarf. But here's the really interesting thing, is that the size, remember the size of a white dwarf was about the size of the Earth. These things, 2 or 3 times more massive in terms of mass, but the size of an average sort of city, about 20 kilometers across. Wow, that's dense. That's real heavy stuff. To the point of 1 teaspoon of neutron star material weighs on Earth 1 billion tons. Jeepers, you thought 15 tons of a scoop, a small teaspoon scoop of a white dwarf was heavy, 1 billion tons. These are the most compact, densest, heaviest objects in the sky, neutron stars. These are the bad boys. Because of that, they're so dense and compact and small, your surface gravity, the gravity when you experience on the surface, it, as you know, is a factor of the mass of an object and how close you are to the center. These babies, they're huge, and this is important for what we're going to be talking about. Very intense gravitational forces on their surface, whereby if you put an object 1 meter above the surface of a neutron star, dropped it and let it go, it would be traveling at 1,400 kilometers per hour when it hit the surface, probably in about a nanosecond later, 1 meter above the ground, just like that. It'd be going from 0 to 1,400 kilometers per hour. Incredible. What would actually happen is, because the forces are so intense, the tidal forces, in actual fact, if it was whatever it was, a tennis ball or whatever you were dropping, would instantly also just get shredded to torn apart because of this sort of the tidal forces, a thing we call spaghettification. So next slide, thanks, James. So that's a little bit about them. So you know about their size, how dense and compact they are. You know they're rotating quickly in intense magnetic fields. Let's talk about the model. What do they think's going on inside these things? I remember someone saying to me, how do they know? They can't even see them. Of course they can see them. They can see them in X-rays, and they can see the effects they have, as you're about to find out. But what they do is they get the laws of physics. They say, look, we've got an idea of probably what's going on with neutron degeneracy under certain pressures. We know how compact and dense these things are and their masses. We can measure mass. So the laws of physics tell us certain things must be going on. So you then match it against your observations of what you see going on in the neutron star, form a hypothesis and see if those observations match that or not. And you constantly refine your model. So this is the current model. It's this purposely that's on this slide is on your screen, so you can go back with more detail, perhaps after tonight, go through that more clearly. But the 3 key points I want to make here is that the neutron stars have a thin, solid crust that are composed of loads of free charged particles, mainly electrons and protons. They are held down by those intense gravitational forces I've just spoken about, but under the right conditions and with the right forces that we're going to talk about shortly, they can be extracted off. And that's part of how all the action starts with neutron stars. So a thin, solid crust with loads of free electrons and protons. Then you move down to your different layers. You've got a deeper layer of crust, and then you started getting liquid inner core and outer core and so on. My 2 points here with the interior, I'm going to glance over this set of slides over here, is that you've got a super fluid, really, really liquid, very little, if any, viscosity, super liquid, super fluid, sort of soup, if you will, of these neutrons, which are neutral, no charge, the neutrons, and they just flowing very, very freely in sort of whirlpools, if you wish, as they remember these stars are rotating, really, neutron stars are rotating very quickly. We're going to talk more about that. So you've got these little whirlwinds going on of these really super liquid whirlpools of sort of soup of neutrons. The second thing is, in the inner parts, you've also got loads of protons, which are positively charged, and you've got, they sort of, because they're compressed, they're what we call superconductive. They're really ultra-conductive electrical currents. And that acts to drive and anchor down strong magnetic fields that come out of these neutron stars. So you've got these magnetic fields coming out of all stars, have magnetic fields, the sun has them, and so on. That's just a natural thing of all these charged particles. You've got these neutron stars are spinning rapidly with these loads and loads of really freely moving around superconductive protons. So they really anchoring down, to able to drive and anchor down magnetic fields. You'll find out shortly, this is really, really relevant, all of this. Next slide, thanks, James. This is getting exciting. So you might say to yourself, why do neutron stars rotate so rapidly? How rapidly do they go? Why are they rotating so rapidly? What's going on there, guys? And you'll say, well, why do they have these powerful, intense magnetic fields I'm talking about? The key to all of this is their progenitors. Remember, these are big stars. These big stars are greater than 8 solar masses. When they go through their red giant phase, they're called red supergiants. They're really, really big, fat stars, whereby these guys' progenitors, these red supergiants, a lot of those, if you got one of those and put in the middle of our solar system, it would take up most of the solar system. It might go out to the orbit of Saturn, even beyond further. You know, and here we are talking about the little wee piddly little sun in the middle of the solar system. These babies are so big, they would consume our solar system. The other concept is, remember we talked about how they all came down, collapsed, and the core collapsed and so on before it exploded. There's a thing called conservation of angular momentum. And James, can you just whip down to the next slide, please? The lady of the ice skating here. And this is the one that everyone can relate to. It's called angular momentum. That's the force at which you're and the speed at which you're rotating around. And angular momentum is a function of the radius of an object and its rate at which it's rotating. And a really classical example everyone can relate to, you see your ice skater on the ice. She's got her arms out and she's rotating around. And then suddenly she brings her arms inwards, reduces her radius, and suddenly she starts spinning a lot quicker because her rate's increased. Because angular momentum is always conserved. So you shrink something down to conserve that angular momentum, it's going to start spinning faster and faster. Back again, James, back to the picture of the big red supergiants. Thank you. So what happens is when it starts to shrink down, it's already been rotating, all stars rotating. You've got these big things from the size of our solar system shrinking down to a size of a town on piddly little old Earth, 20 kilometers across. That's a huge drop in radius. It's just, you can't even get your head around it. So immediately the spin rate has just gone up by a huge, huge factor, whereby neutron stars are quite happy rotating around up to over 1,000 times per second. 1,000 times per second. That's how quick neutron stars are rotating. And that's why the progenitor was the size of the solar system. It's suddenly been shrunk down to the size of a small town. The other principle applies to the magnetic fields. Most stars have magnetic fields going around them. Same principle. It gets shrunk down. Suddenly those magnetic fields suddenly become more intense and more powerful, whereby the magnetic field strength on most neutron stars is up to 1 billion times that of the magnetic field strength on the sun. James, could you please flick through past the ice skating onto the next run? The next slide is, so you might be saying, okay, I understand that. Yep, I get it. They rotate really quickly. And I know now why. It's conservation of angular momentum. Do those rates change at all, or are they set in concrete? For our sort of speed, most of the time, they are pretty much set in concrete. You can set your clock by them. In fact, that's what they do set clocks to sometimes with these pulses. But the bottom line is, yes, they do. They do change. They can slow down and they can speed up. The next slide. Thanks, James. So they're just like us. With time, they slow down, they lose energy and slow down as well. And that's the natural history of neutron stars. That's how they do a lot of energetic events, as you're about to find out. Energy is conserved. How do they get rid of that energy, or what makes up for the loss of energy? They start slowing down. And that term is known as spin down. So you might say, okay, that makes sense. They're slowing down, spin down. I get that. Is there a such thing as a spin up? You betcha boots there is. James, next slide. Thank you. So this is interesting when you're starting to get close binaries. Remember with the white dwarfs, a lot of the action was happening with close binary systems. Same here with neutron stars. It all happens here. So what can happen here is you've got your red dwarf, your red giant, once again, right next door this time to a neutron star. The material goes across, and you know now it's the laws of physics because of the whole rotational rates. A nice little accretion disk happens. And as the material feeds onto the neutron star, it can give it a bit of a nudge forward and start speeding it up. And that's called spin up. And it's that process that gives rise to what they call millisecond pulses. Don't get too worried about the word pulses. They're neutron stars that pulse, obviously. So I'm going to talk about that shortly. But the bottom line is they're called millisecond pulses of neutron stars. That's how they get that fast. They get spun up by a red giant companion feeding material onto them. James, would you be kind enough, please, just on to the next slide. It's called glitches. There's a process called glitches that happens with neutron stars. And that's where you can get, and they do observe it, neutron star might be spinning around at this crazy rate, but nice and regular. And all of a sudden, without warning, it just gets a jolt out of the blue and it suddenly speeds up. And it's also been noted, sometimes it can then shortly afterwards get another jolt and slow back down again. They are called glitches. And the general idea or theory with the models, probably what's happening here is you're getting these whirlpools of superfluid neutrons that we talked about, very superfluid. And James will probably point my little sentence out there. Then James will go down, please, and just put your cursor over the inner picture and that first little pale blue line. And you can see what happens is a whirlwind from the inner part of the crust slips out, grabs hold of the thin, rigid outer crust that we talked about early on, and gives it a bit of a flick and flicks it forward, a bit of a jolt. And it's a quick glitch or a spin up. What happens then, that same process, you get another little second whirlpool of these superfluid neutral neutrons that's coming from the inner parts of the core, that too latches itself onto that thin, rigid crust of the neutron star and does the opposite, pulls it back, jerks it back again, gives it a quick sudden jolt or spin down backwards again, and that's another glitch. It's an interesting concept, and if you're having trouble trying to think about it, it was actually the HCAS's president, Jay. We were talking about this one day, and Jay commented a really neat analogy that she used, and I thought it was perfect. It's like a twister or a hurricane on Earth. It's elongated, whirlpool. It has properties of gas and liquid. You got water, rainwater in there. You got water vapor in there. And it's, what a twister does. It moves, it darts. It's very, very mobile. It darts here, darts there. And what does it do? It can often attach itself. It'll pick up a house or a motorhome. It'll dart somewhere else and drop it down there as it attaches to the earth again. So it's a whirlpool spinning very, very quickly, little resistance, sort of fluid, gaseous sort of nature, and it can quite happily dart around and attach itself from time to time with rigid surfaces. And that's a really good analogy. And that is the general idea, the general model suggests what's going on to explain these glitches or sudden jolts forward and sudden jolt backs of these neutron stars. Next slide, thanks, James. So, I mentioned to you that they have very powerful magnetic fields. And one of that reasons is, remember I talked about how it gets concentrated? Well, the magnetic flux of any object or star is related to the inverse square of its surface area. So remember I talked about those stars, those super red giants that take up the solar system. You imagine the surface area of one of those. Suddenly it gets shrunk down to the surface area of a ball the size of an average town. imagine the fact that the huge factor of reduction in surface area, square that, and you've got the strength of the magnetic field of these neutron stars. You can suddenly see it's becoming obvious, isn't it? These guys are highly magnetized, really strong, intense magnetic fields as they spin around about 1,000 times per second. Now, there are some neutron stars that are ultra, ultra, ultra magnetized, huge, really strong, much more than that. They're called magnetars. They're given a name. They're called magnetars. They seem to be a class of neutron stars out on their own. And James, next slide, thanks. And the relevant thing about magnetars is that things called star quakes occur on them. And that's what happens then is a magnetar might go through natural spin down process, getting a little bit older, like us all, starts to slow down a bit. And that spin down process starts to have an effect on that. Remember we talked about the crust was rigid and it's thin. And what happens when you're starting getting changes in rotations and so on? It's just like on Earth things happen. You get little stress fractures in that thin, rigid crust. You're talking high energies here, highly magnetic fields, extreme conditions. And when those little star quakes, if you will, little fracture in the crust occurs, you get a sudden burst of high energy, very short, sharp energy. And that elicits itself is what they call a short duration gamma ray burst. A gamma ray burst is literally that, a quick burst of a gamma ray. And you'll probably recall our talks on light, how gamma rays are the most extreme forms of light, extreme form. And you get a quick burst of them. Short duration refers to less than 2 seconds. So you've got these extreme conditions, slowing down, quick stress fracture occurs, a sudden burst of huge amounts of energy that can be seen right across the galaxy. They're called short ray gamma ray bursts, and they're because of star quakes in these magnetar stars. So that's relevant why I raised the issue of magnetars. Next slide, thanks, James. Then we're starting to talk about pulsars. And there's 2 different types of pulsars with neutron stars, which I'm about to explain. And as you'll see, there are radio pulsars and X-ray pulsar neutron stars. The latter are where you get a close binary system again. And as you'll see, these radio pulsars, you get those just when you get a neutron star on its own. So here's why. I'm going to read off my slides here. Your neutron stars rotate extremely rapid. You're fully aware of that. We've talked about how they've got powerful, intense magnetic field lines. And I've used the word well anchored. Why? Because we talked about the inside, that those dense, really superconductive fluid, loose protons flowing in there. They generate electric currents and magnetic fields, and they anchor those fields right down hard into the innards of these neutron stars. And what is the crust made of? We talked about that those magnetic field lines come out of a thin, rigid crust of free electrons and free neutrons that can be extracted under the right conditions. So we've talked all about this and what we're leading up to. Next slide. Thanks, James. These magnetic field lines, well anchored in these neutron stars that are spinning round and round and round and round 1,000 times a second, what do you get from your physics classes? What did your teachers tell you you get when you start spinning around in magnetic fields so quickly? What do you get? Electrical currents. So suddenly you've got really powerful electric currents coming out of the surfaces of these neutron stars, going around and enveloping right around the neutron star. And they create like a magnet, a north pole and a south pole. Those electric currents are pretty powerful and very, very strong, much extreme than you could ever imagine on Earth. What do? They pick up those free electrons and free protons, mainly electrons. They pick them up off that rigid surface, start accelerating them to the relevant magnetic poles of the neutron stars, and then start shooting them out at those from both poles. You call those bipolar jets, meaning you've got 2 poles along the axis of rotation of the neutron stars. You've got jets firing out, and you've got electrons that are now being accelerated to close to the speed of light. The astronomers use the word relativistic. And the word relativistic means approaching the speed of light. So you've got these electrons that have been lifted up off these rigid surfaces, accelerating through these electric fields all being funneled and directed to the magnetic poles, all being spat out in these bipolar jets. That gives rise to synchrotron radiation or radio waves. And you're probably thinking, synchrotron radiation, he hasn't talked about that tonight. Next slide, thanks, James. We're going to just take a little side step for a minute. The next slide should be headed up synchronized radiation, synchrotron radiation. Synchrotron radiation refers to the process occurs when charged particles, like electrons and neutrons, are spiraling around a magnetic field line. As they do so, they emit light. They just do that because they're accelerating. And that's called synchronous radiation. You'll know when things get hot, as you heat them up, the molecules jiggle more and more and they emit more and more light at higher energies. That's called thermal. This is called non-thermal because the radiation's got nothing to do with how hot the particles are. It's just that the charged particles, when charged particles move through magnetic field lines, they experience a force. And that force causes them to spiral round and round and round and round those magnetic field lines, and which is a form of acceleration because they're changing their direction. That's part of velocity and acceleration. Because they're accelerating, they're naturally emitting light. And it's a light that has a certain characteristic about it. When you put it through, you observe it with your telescopes and so on, the astronomers can do an energy spectral diagram of it and can readily identify that synchronized radiation that's going on. It can go right across from radio waves right through to X-ray rays, but as a rule, it's usually far, far more prominent in radio waves. So if we just go back a slide then, so then James, back that previous one. So my bottom line is there, you start getting synchrotron radiation, which is prominently in radio waves, coming out of these magnetic poles. So James, would you be kind enough, please, to move past synchrotron radiation to the next slide? So what you get then, and where's my torch that I had here tonight? Here it is here. I wanted to show what's going on. We start seeing if the magnetic poles are not aligned with the rotation, the axes of rotation, you start getting the light beam and radio wave start sweeping around across the sky, and it's much like a lighthouse. And I want to show you what that means. If you see my torch here, say that was a radio wave coming out of the magnetic lines in the magnetic poles of the pulsar. I start spinning it around. What do you see? If you're on Earth, you're seeing a pulse of light going round and round like that. But notice the light is still on, and that's what's going on with these babies. You're still seeing that the synchrotron radiation is continuous, but when we observe it from Earth as it sweeps around, James, could you just move to the next slide, please? I seem to have lost your picture in there, but anyway, you'll see I've written down there, as the beam sweeps across our view, we see pulses of radio waves analogous to a lighthouse beam sweeping around, and we call those pulses or radio pulses. And that's a single neutron star on its own, just doing its thing. The neutron stars are all pulses neutron stars, and are all neutron stars pulses? All pulses are neutron stars, but not all neutron stars are pulses. Why? To be a pulsar, it's got to be a relatively young neutron star, like sub 1 billion years, or rather 1 million years, whereby it's got enough speed and enough energy and enough magnetic field strength, field lines to generate that whole thing going on. The other thing is we only see them as pulses if it happens to be that beam of light or synchrotron radiation is coming in our field of view. If it's not, we don't see it as a pulsar. Next slide, thanks, James. So we now move on to X-ray pulses. You might, really, how does that happen? And this is a circumstance where you get your red giant sitting next door to the neutron star, material goes across into the accretion disk. You've got some pretty intense gravitational field going on here, much, much more than what you had going on with your white dwarf, because you've got something far more compact and dense. Next slide, thanks, James. So the inner part of the disk, instead of it just quietly falling off at random anywhere on the white disk surface, as it does in the white dwarf. Here, you've got these really strong magnetic field lines coming in off these neutron stars. And as the inner material of charged particles, it's usually coming from red dwarf, it's usually hydrogen, protons, charged particles. As they start falling on, they get captured by the magnetic fields. And the magnetic field lines then direct or funnel those charged particles coming in at huge velocities and dumps them at the magnetic poles of the neutron stars. And when they hit the surface at huge velocities, remember I said if you drop something just from a sheer meter, it'd be traveling at 1,400 kilometers per hour as it hits. It hits with an almighty bang. A lot of energy is released, and that is released as X-ray radiation. So what you're getting is constantly X-ray radiation, once again, shooting off at the magnetic poles. If those magnetic poles are not aligned with the rotational axis of the neutron star, you get a nice sweeping beam across the sky of X-ray radiation. And if we happen to be in the line of sight of that sweeping beam, we see an X-ray pulsar. So a radio pulsar is when you get a young neutron star out on its own, giving radio waves, and X-ray pulsar is when you get a young neutron star that's emitting X-ray light, but it's in combination with a binary. Next slide, thanks, James. And you'll see here, the other exciting thing that can happen with close binary systems is when you get two neutron stars together going round and round. They lose energy, and eventually they get closer and closer, and they merge. What do? They create gravitational waves. In the last 5 years, that's become very topical. It's a whole field of astronomy, very exciting, that's opening up. When those two neutron stars collide, next slide, thanks, James, you'll see the periodic table of elements there. Collision causes what they call a kilonova, which is an explosion 1,000 times brighter than nova, hence the name kilonova, but it's a powerful explosion, and that creates a whole big stack of heavy elements, important elements in the universe. And you'll see there on that picture that James will point out, the orange block there says merging neutron stars, and have a look at where it says orange in the bottom of the periodic table. You see those are all the elements that are predominantly made by two neutron stars colliding and causing a kilonova with this explosion. So next slide, thanks, James. And you'll see there's a nice summary of neutron stars. Their progenitors were high mass stars between 8 and 20 solar masses. Nuclear fusion stopped at the core. The core collapsed itself. Supernova explosion as the outer layers get sheared off. And you get a compact, dense star, dead star, neutron star, that's rotating extremely rapid, over 1,000 times per second, with a really intense magnetic field. You get these supermagnetic magnetars. They give rise to star quakes, repeated brief, short gamma ray bursts. You get these radio pulsars from single neutron stars, the X-ray pulsars from a close binary system with neutron stars, and you get the mergers. Moving ahead, we're now going on to stellar black holes. Just a brief summary of those. Next slide, thanks, James. That should be the title. After that, we're moving on to you'll go to the next slide, and that's just giving that central diagram you've seen a few times now today, and James will point out that bottom row there. You'll see the star goes supernova, 8 to 20 solar masses, the core collapses into a neutron star, greater than 20 solar masses. Here, the force behind, because a higher mass core collapse, it goes past electron degeneracy. It then goes past neutron degeneracy. This time it's got the power or the force to overcome the polar exclusion principle and actually just starting to merge the neutrons. What happens beyond there, we don't know. You can't see. It's called a black hole for that reason. The laws of physics seem to break down. Still a big field of physics. But you overcome those forces. You get some singularity, some infinitely dense, compact object known as a black hole. Next slide, thanks, James. And you'll see here that what happens is that the fabric of space-time in these black holes gets totally warped inwards, where essentially light cannot escape. And that's the name black holes. All sorts of things interesting happen because of this intense distortion of the fabric of space-time. It's beyond the scope of this talk. I really want to move on. we'll do it another time. James, to the next slide, thanks. Because once again, what happens with black dwarfs? How, with these black holes, how do you see them? You can see them indirectly through, once again, having a close binary system. Here's your red dwarf sitting next door to your X-ray, to your your black hole. The accretion disk forms. This time, the material as it falls in, we can't see anything further beyond that event horizon as it falls in. But because the sheer force of the gravitational forces, as the accretion disk material is approaching, getting closer and closer to the black hole, that material is getting compressed to such amazing forces, or just the material getting compressed before it enters the black hole emits bursts of X-rays. So they see in the sky with the X-ray telescopes just certain spots. We just get irregular random bursts of X-rays, and often that's a clue that you've got a black hole sitting there with a close binary. And often they can actually see that red giant or that red supergiant slowly accreting material that's going into the black hole. Next slide, thanks, James. And you'll see there, the next other thing exciting that can happen with black holes and these close binaries, you get two of them together, they can quite happily merge as well. They give rise, once again, to gravitational waves, which, as I mentioned, the last 5 years, this is a whole field of astronomy, very exciting that's opened up. They get a lot of information from those gravitational waves, once again, beyond the scope of this talk. Next slide, thanks, James. So summary of black holes vary from very high mass progenitor stars, greater than 20 solar masses. After the supernova explosion, that's your condensed core. And once again, the action happens when you're in a binary system. You can get those bursts of X-rays, X-rays coming out of that system, or you can get a merger and a gravitational wave. Next slide, thanks, James. Next slide again after that. We're just going over a quick summary now. You've probably seen this slide too many times, but what I'm going to do is point out, if James can, on the right-hand side there, where it just goes over the stellar corpses, you'll see the white dwarf, which on average is about 0.6 solar masses, that collapsed core. You've got your neutron stars, which are about from 1.4 to 3 solar masses. They're unstable above that, and they're about the size of a small town. The white dwarf about the size of Earth, neutron stars about the size of a town, 20 kilometers across, and then you get the black hole stellar corpses. They are greater than 3 solar masses, and of course they're infinitely small. We don't really understand where things go from there. Next slide, thanks, James. Another just key message here, the whole concept of degenerative matter. It is an important concept, and it's a quick, easy one to understand, but it is important in the context of these stellar corpses. You'll see here in the white dwarf, material gets all distorted, not strong enough to bring the nuclei together though, but it just sort of leaves a disordered, disformed sort of type of pattern with electrons shooting around, going amok among neutron stars. The neutron star, higher mass core, it does overcome that resistance force, drives the electrons into protons to create just a big ball of neutrons trying to avoid one another. So it's called neutron degeneracy. And then the black holes with the core greater than 3 solar masses, that overcomes that pressure and creates these infinitely dense black holes. Next slide, thanks. And James, so how do stellar corpses have fun? Yep, the white dwarfs give rise to your novae and your supernovae type 1s, and of course mergers. Your neutron stars give way to radio pulsars, X-ray pulsars, and also mergers, which give rise to nuclear synthesis, just a fancy word to describe the production of a lot of new elements. And of course, stellar black holes, once again, you get a binary system. They give rise to your X-ray emission and your mergers. Next slide, thanks, James. And so when you're next, I was going to say when you're next at home, but you're already at home. So when you're next chilling at home, bit of homework, go and look more into white dwarfs, what they're about. Do a study of them. Have a look into your planetary nebula. Why? Because, hey, that's going to be the fate of our sun one day, in about another 5 or 6 billion years. Our sun's 1 solar masses. Remember, white dwarfs come from anything from 0.8 to 8 solar masses. Next slide, thanks. We're coming near the end of it, so I'm sorry about the technical glitches we've been having tonight. We'll get them sorted, that's life. So stellar corpses, yeah, when a star dies, the party is far from over. These guys are just kicking in. They're starting to party. So thank you very much for watching. Our next slide, thanks, James. Any questions? Can you talk to me, James?
Okay, can you hear me, Chris?
I don't think James can talk to me. Anyway, James,
Can you hear me, Chris?
you want me to ring you, James, and see if there's any questions? Oh, there you are, James. Can you see and hear me?
I can hear you, yes.
I can't hear you.
How about now? Can you hear me now?
Oh, are there any questions? I can't hear you, James. You're welcome to phone me. No, you can hear me.
So no questions.
No questions.
Just see if I'm on mute. Okay. Let's try
James is sending me a message. See if I'm on mute. No, built in.
So I don't think I am.
I can hear you now.
Ah, great. There we go.
Yep.
Okay. So are there any questions out there? I don't see anything in the chat. So if you've got a question, pop it in the chat there. So Chris, how are these? I mentioned in the news about the F-bots, Cow and the new one that they've sort of discovered. How does that kind of fit into stellar corpses? Any ideas?
No, look, I haven't really been. I probably been busy this week, and I haven't looked a lot into that, to be honest, James. So I'm sorry to say I can't totally help you there. Yeah.
They're quite interesting. I'd be quite interested in these things which are very transient, like the fast radio burst. And
well, interesting enough, they think that neutron stars and white dwarfs colliding is a prime contender for your fast radio bursts. So, and as you mentioned, these other things, these quick bursts, they usually do involve stellar corpses in some way, because the very nature of the stellar corpses, they're compact, they're dense, they've got powerful gravitational fields. Because of that, you get them close to something else, and whammo, you get some interesting reactions and high energy events, some of which are short, sharp bursts, like your gamma ray bursts and so on. So absolutely, it gives rise to high energy physics.
So a lot of those big ones that are releasing huge amounts of gravitational waves. So we can pick that up on the new gravitational wave telescope.
Yeah, absolutely.
Yeah, what it's called.
It's another form of astronomy. You got radio astronomy, X-ray astronomy, neutrino astronomy, and now you've got gravitational astronomy. And you get information on the one event from all different sources through analyzing light, analyzing neutrinos that are pouring out of it, and analyzing the distortion in the fabric of space-time through your gravitational waves. You can start building up some pretty good pictures and start refining some models.
So there's a question here from Ben. He says, where is the closest known neutron star to Earth, and is it observable with visible light telescopes?
Yeah, a good question, Ben. Great to hear from you. The closest actually, just jump ahead a little bit. The closest white dwarf is the Sirius B. In the summer sky, you get the Canis Major, the brightest sky in Canis Major next to Orion. It's a binary star system. The big one we see is I think it's a big A-type star, but your small one is actually a white dwarf. To your question, Ben, I believe it's actually the Crab Nebula in Taurus that you see in summertime. That is and right at the heart of there. That with this one of the earliest slides had a picture of that in X-ray wavelengths, and you could see the little dot that James pointed out. That was the neutron star, or it's a radio pulsar. I don't have the top of my head how far away that is. I'm unsure. I can't tell you exactly, but I'm pretty certain that's our closest pulsar. And in answer to your question, sadly, you can't see it through your normal optical telescopes. It's most predominant because you're talking high energy events. It's predominantly identified in X-ray wavelengths. It does give off a bit of a stellar wind, which I didn't comment on. That's predominantly in X-ray. And then you've got all your effects around the accretion disk and stuff. Most of all that stuff is in X-ray. You've got those high-speed electrons coming up off the surface. So mainly it's high energy physics. It is able to be seen through a telescope, but an X-ray telescope. So now, having said that, with a good optical telescope on a really good, clear, dark night, you look into the constellation Taurus, and hopefully you got a go-to, or otherwise use your star map. You can look at it, and with a bit of patience and getting adapted to the dark, yes, you can see the Crab Nebula with your own eyes, but you wouldn't see the neutron star in the middle. It's too small for that, and it really doesn't emit enough optical light for that. So good question, Ben, and yeah, very good question, my friend.
Now, I remember the one evening at Auckland Astronomical Society, we were looking through the scope, and we could actually see Sirius B.
Right, wow.
Which was really, really good. It took a lot of hard work with the guys, but everything was just perfect.
The closest white dwarf. Yeah.
So, yeah, you can see the white dwarfs with a very, very big scope. Have you been to AAS and seen their scope? I'm not sure what size that is. Can you remember?
50 centimeters, I think.
Something like that.
Yeah,
and even then, it was really, really difficult to bring up that image, but yeah, we managed to do it. So those are visible with the right equipment. Because I believe we can now see where there's the closest black hole. It was about a week or so ago. I can't remember all the details.
Yes,
apparently, naked eye.
Yeah. Yeah.
I mean, you can't see the black hole, but you can see where it is.
You insinuate where you get to see it indirectly through all these other events that are happening around it.
Yeah. So yeah, there's a whole lot out there that we definitely can see, except for those little neutron stars. I mean, those things are tiny, tiny, tiny. Like you say, about 20 kilometers odd across. Yeah, so obviously anything that's a decent distance away, we're just not going to see it, no matter how bright it is. Of course, radio telescopes, yes, you will. You can see them in the radio spectrum. Any other questions out there? I think that is it.
In the meantime, we'll have to sort out technical problems. I think, to be honest, I think it's something to do with this Apple, with the Zoom. It just, you get an upgrade, which has happened, and it just doesn't trust any software and just blocks everything.
Yeah, so
we'll sort it out.
For anyone who's
close off the Zoom meeting anyway, then, James. Good night, everybody.
Good night, everyone, and we'll see you in 2 weeks' time. We've got a very good guest speaker on. Heratina Mogasanu, who's the astrobiologist. She's going to come and have a chat to us about something. I've given her free rein, so it's going to be a good one. I've heard her speak numerous times, and yeah, well worth doing. We'll of course be advertising that in advance. Thanks everyone for attending. Thank you, Chris, for your talk. As usual, very, very well done.
I think between the team, but you doing the slides and me doing the talk, we got through it. Anyway.
Technology, at least we were able to do that. It wasn't a total disaster.
Yeah, all good.
Okay, so I'm going to wrap it up there. Thanks, everyone, and have a good evening. Bye.
That's good. Were you off now, James?
Yeah.